All right, here's our friction ramp example problem. So we got a ramp with an 8 kilogram mass that's 1.5 meters from the bottom of the ramp. They give us the coefficients of static friction, the coefficients of kinetic friction. And here's the question. The angle is increased until the block starts to slide. How long will the block take to reach the bottom of the ramp once it starts to slide? So I got two blocks here. You can see here, as I increase the angle, eventually one starts to slide. This other one did not, because we have a higher coefficient of friction. But even this one, once we get steep enough, it will start to slide. And then once it slides down, it will accelerate down to the bottom of the ramp. Now, friction is a little bit tricky. It's really tricky to measure in real life. So you guys are lucky that we're not going to do this lab, because it gets a little bit messy. But we are going to do the problems here. So the materials, whether it's a slides freely or if it's a little bit stickier like this rubber, it is how hard it is to slide is identified by this coefficient of friction. So remember, this coefficient of friction relates the force that something's pushed together with how much it's starting to slide. So obviously, the harder you push something, the harder they're going to stick together. If it's very light, it slides easily. If you push things together, you get a lot more friction. And so that comes from this equation that we're going to start with, that the idea that the friction force is equal to the coefficient of friction times the normal force. Now, the normal force is how hard the surfaces are being pushed into each other. So if we draw our forces here, we can see here that we're going to have a normal force. We're going to have a friction force, and we know it's going to be up the ramp because gravity is going to try to pull it down the ramp. And then we have a force of gravity. Now, right away, we're going to start with our components. So we have Fg normal and Fg ramp. Again, Fg normal is down into the ramp. Fg ramp is down the ramp, along the ramp. And from here, we can start out with our equations. So from the last video, we found that the normal force was going to be equal to Fg normal, which turned out to be mg cosine theta, because here's our angle theta, and Fg normal is adjacent to that angle. And so we can see here that we can put this into our friction equation right away. And we see that the force of friction is going to be the coefficient of friction, mg cosine of theta. Okay, now this is interesting because it says as cosine of theta gets bigger, the friction force is going to get smaller and smaller. So we can think here, we got this block. When the block is flat, the angle is 0, and Fg normal is equal to the normal force. And that's when the maximum friction. The more we start to tilt the ramp, the smaller and smaller the force is pushing it into the ramp. Eventually, when the ramp's vertical, there's no force pushing this into the ramp. And so there is no friction because there's no normal force pushing it in. And that shows up in this equation. If theta is 90, cosine theta is 0. If theta is 0, cosine theta is 1, and the normal force is just equal to mass times gravity. So those equations work together. And then we have our other equation, which is in the parallel to the ramp direction, where we said that if we say again down is positive, when we have our new coordinates frame, we have Fg ramp minus the force of friction is going to equal to the mass times the acceleration down the ramp. So we can put our acceleration as the positive direction down the ramp. So now these equations line up with our picture. We got the right directions. The minus sign becomes the force of friction is up the ramp, which is opposite to what we said is positive. And we can put these things together now. So the force of gravity down the ramp is going to be mg sine theta. The force of friction is going to be mu mg cosine theta. And that's going to equal to the mass times acceleration. Okay, but there's a little bit of part in here that the friction force is never going to make something move. So the friction force is going to hold this steady until the gravitational force down the ramp is bigger than it. So the friction forces are kind of funny that way. They don't just start pushing things up the ramp. They only oppose motion. So first off, to find out when this is going to slide, we need to know when the friction force is smaller than the force of gravity down the ramp. And so right now it's not sliding, so we could say at rest that the force of friction is going to be equal to the force of gravity down the ramp. Okay, so when we write our force of friction in here, we get mu mg cosine theta is equal to the force of gravity down the ramp, mg sine theta. Now, since we are at rest here, that means we need to use the static. Rest means not moving or static. So we are going to use the static coefficient of friction. All right. And now we need to solve this. We've got to figure out what angle is it when these two are equal to each other. And that'll be the angle where things are just about to break loose. So right here we can see that the masses are going to cancel out. And we get mu g. Well, the g's cancel out too. So we get mu is going to be equal to sine theta over cosine theta. So again, we got to think here, well, sine over cosine, what is that going to be for us? And you can think of our rules. What's sine? We can remember over here, we got this whole SOHCAHTOA. This is the way I always help remember it. SOHCAH, this is you guys' favorite. So we got opposite over hypotenuse, opposite over adjacent, and opposite over adjacent. So if tangent theta is equal to opposite over adjacent, hopefully you guys can see that it's going to be the same thing as sine over cosine, right? And you should remember that from your trig rules. So turns out here, even though we have theta showing up twice, we can use our trig functions to solve for this one, tangent theta. Or to reverse it, the angle where things are about to start to slide is going to be the inverse tangent of our coefficient of static friction. All right, so that'll tell us the first part. That will get us our angle when we're supposed to slide, because that's the part we'll need first. Okay, so for here, we could go into decimals, we could figure out what these are going to be, and we could solve for it. We'll save that till the end. All right, once we know the angle where things are going to start to slide, then we have to go to a new version, because here we have our at rest, which is static. But once things do start to slide, we go past the angle where these two forces are equal. And once we go past that angle, as we increase the angle, the friction force gets smaller and the gravitational force down the ramp gets bigger. And so once we go past that angle, then we'll have sliding. Now, once things start to slide, we are in the kinetic zone. Kinetic is another word for motion or moving. Things are moving if they're kinetic. And in that case here, we have to rewrite this equation. So we got mg sine theta minus mu mg cosine theta is equal to ma. Now here, we're going to be in the kinetic coefficient of friction range. So now the value switches. When things start to slide, we go from the static regime into the kinetic regime. And now the kinetic friction is always smaller than the static friction for reading problems we're going to do. Hopefully you've seen this in real life. If you're pushing on a cardboard box, it's kind of hard to get to slide, but once it starts sliding, then it gets a little bit easier to keep it moving. That's because you break it loose. And when you break it loose, it becomes a little bit easier to slide. So now we can put this in here. We need to figure out what the A is. We can see here that the mass actually cancels out in all these. We can divide both sides by m, divide these by m, the m's go away. And we can simplify this out here. We get g, because that's common to both terms, times sine theta minus mu cosine theta will be equal to our acceleration. All right, now we know what the theta is because we can solve for it. And now we need to figure out, once we have the angle in g and the coefficient of friction, here again we're going to be in the kinetic world because it's sliding, we can find the acceleration. And so for the last part here, how long will the block take to reach the bottom? Well, we know the distance, we know the acceleration, we know that the initial velocity is going to be 0 because it's starting in the static world. And so if we put these together here, if we know A, we know VI, we know delta x, and we're trying to find delta t, or how much time goes by, it's pretty easy to see that we're going to use our equation. Delta x equals VI delta t plus 1/2 a delta t squared. So this term will go away. We get delta x is equal to 1/2 a delta t squared. And solving for delta t, we get 2 delta x. The 2 comes up, the a comes down, equals delta t squared. If I take the square root of both sides, I get rid of the square. And so now we have an answer for delta t. So if we substitute all this back in here with a and our theta, well, we can see here that we're going to have the square root of 2 delta x is delta x is going to be our 1.5, all divided by our a, which is going to be equal to g sine of, now we can put this in, tangent -1 of, we got the, we got to put this in here, we got the static coefficient of friction, so I'll just write this here, mu static. So that's the sine. Now we got minus the kinetic coefficient of friction times the cosine of the inverse tangent of our static coefficient of friction. And that's our A. All right, so the next part here is we can put that in and solve it. So to do that here, I'm going to pause this and I'll go to the desktop. Okay, so now we want to find our answers here. Whenever using decimals, again, make sure you put it in degree mode. Things get easier. And first we have to find the angle. So we have the inverse tangent. Oops. Tangent. Let's see if it lets me do it this way. Inverse tangent of our static coefficient of friction, which was 0.35. All right, and so we can see this gives us a reasonable angle, about 19 degrees. All right, once we know that, then we can type in our whole equation here. So we get our 2 times 1.5. We need to divide that whole thing by 9.81. That's our g times the sine of, now we could put this exactly in, or we could put the angle in. Just for fun, I'll just keep this in here. I'll paste that in. And then we have minus the kinetic coefficient of friction, 0.25, times the cosine of that angle. And then we look it over, and we always want to make sure that these things match up. And it looks pretty good. So it gives us a time of about 1 second to reach the bottom. So we got to think, is that reasonable? 1 second to travel 1.5 meters. You know, that's in the ballpark. Seems like it could happen. And that would be a good answer.